prepare for the next video we're going to watch, I've kind of prepared a note-taking guide for this video, but the first problem is kind of a review, and I do know that a lot of us remember how to set up an exponential function based on the information given and then just plug numbers into that, but I actually want to step back and remind us how we actually constructed that and think about the math a little bit deeper from when we first learned this, because that will help apply and understand the formulas that are put in this video. So if we have 318 people and we're having 12% growth over time, and we want to know how many are infected after 5 days, the natural way that most people are going to be drawn to solving a problem like this is to start with my number of people that are already infected. Well, and then by tomorrow, how many people are going to be infected? Well, since it's 12% growth, that means we're needing to add 12% on, which is 0.12 as a decimal, right? Of 318. So 0.12 times 318. That's like the natural way to do that. And then what we're going to get out of this, just so you remember, is, just if you calculate it, is 356.16. So about 350, let's just round up, 357 people or so. Okay? But how am I going to get day, right? So day 0 is 318, and day 1, let's write this in a line here. Okay. And day 2, well, day 2, I'm going to be growing 12%, but remember, it's 12% from the previous day. So I'm actually going to have to take this previous number, 357 plus 0.12 times 357, and then recalculate that for day 2. And again, I took the liberty of doing this ahead of time, and you get about 399 people if you do that. Now, of course, you can kind of see that then I repeat, and to get day 3, I take my 399 and apply that in the same way here, and I could then just keep going until I get to day 5. But that's very tedious, right? And that creates maybe a need or a want in us, like, isn't there a better way? Isn't there a more direct way that I can figure this out? And hopefully remember that, yes, there is. The funny thing is, this turns out to be a recursive way of doing this. And again, that's oftentimes the more gut feeling we have. And this is actually just like calculating tax, let's say. If you purchase something at the store that is $318, but there's a 12% sales tax, well, then you're going to pay about $357 in total for it, right? So this really concept this applies. Now, of course, tax is not going to have exponential growth to it or something like that. But like, one tax calculation kind of relates to this. But again, if I was day 2, it refers back to day 1. And then to get day 3, I'm going to have to use the end result from day 2. And I would have to keep going through this. Now, in terms of functions, just to remind you guys, this helps us see this, that there's a little bit more of a commonality happening. If my f of 0, in this case that was my initial number of people, was 318, well then to get the first day, I have to take the previous day plus 12% of the previous day's number. And then to get the day after that, I just add 12% of that previous day onto itself. But again, what that is the new number, which is f of 1. Okay, so whatever I got out of there applies to here. And you can see that that's just what's happening the whole way through. Okay? And then eventually, after 1, 2, 3, 4, 5 calculations, we can finally answer what day 5 is going to be. So if I wanted this process to be generalized, what I could say here is, let's see, f of n, how does this input relate to that input? This input, I use the previous one, right? So I basically have f of n minus 1 plus 12% of f of n minus 1, right? So to get any output, I take the previous one and add 12% of that previous one. And that continuously lets me get the previous output. Now, if you actually realize that there's an f of n minus 1 contained in both of these terms, I can factor it out and be left with 1 plus 0.12, which then ends up being this. So what I get here is, I have the previous output times 112%, 1.12, but that makes sense, right? Because next year I'm going to have, the next day I'm going to have 112% of the previous day, right? And then the day after that I'm going to have 112% of that previous day. So it's purely recursive. Here's actually a direct, not direct, but a recursive formula that will allow me to figure out how this builds. But that's still not like as useful as a direct formula. But the good thing is, since every single time I have 112%, 1.12, being multiplied to the previous input, then to the previous input to that, the previous input to that, hopefully you remember what happens there is, we're actually accumulating powers of 112, right? So if I wanted to have f of 10, let's say, I could actually go all the way back to f of 0, and I could say, well, it's f of 0 times 1.12 times 1.12 times 1.12, but how many times am I multiplying that on there? I'm going to multiply that 10 times. So that recursive formula helps us actually realize that we're essentially, we can go all the way back to the beginning and then just multiply 1.12 however many times. All you got to do is realize that it's the same amount of times as whatever your input is. And therefore, actually f of 10 is much easier to see that it's f of 0 times 1.12 to the power of 10, because we have 10 of those multiplied to each other. And that's really nice for us, because what it tells me is, if I want an output, I take my initial output, and this right here, okay, represents my growth rate, of 12%, okay? So it's just this 0.12 portion. Now, of course, that 1 is just there because it's like 112%. So let's lead into the actual final closed form rule for these types of situations, and we can then use that to help ourselves understand this COVID-19 situation. So we've gotten used to using the general exponential function format. Okay, so y equals ab to the x, or in this case, if we're using n, f of n equals a times b to the n. And we've we've learned that a is the initial output, and then b represents, our growth, and then we go from there. But now we're going to shift gears a little bit, and we're going to talk about specific situations like this. We've learned about money situations, anything that has an exponential growth, and you're given a percentage to it. Okay, as we've talked about a moment ago, a better closed form rule for this is to put it in terms of this: f of n equals f of 0, and again that just means my initial output, times, remember, 1 plus r just means 100 and whatever percent. So in this case our r is 12%. So really, if I want to, in my case, write a formula for this that's closed form, my f of 0 is 318. And 1 plus r is 1 plus 0.12 to the n, excuse me. And so therefore I have f of n equals 318 times 1.12 to the n. And if I want to know that number, then 318, 5 days, 318 times 1.12 to the 5th power. And if I do that, I'm going to actually go ahead and cheat again, because I did this ahead of time. That's going to be approximately 561 infected people after 5 days. Okay? Now we're going to actually introduce some of the notation that's used in the video, just so that it doesn't confuse you too much, and we're going to talk a little bit more deeply about what some of the variables mean in that situation. really what we're asking right now is, the main thing here is, this 12% growth, how is that growth calculated in the first place? And in these virus situations, that entirely depends on the probability of people getting infected and how many people get infected if you come into contact with them. And so we're going to dive deeper into that right now. So we've seen the general formula for anything that's growing exponentially if you're given a growth rate for the closed form rule, but let's take a deeper dive into a formula that you're going to be seeing in the video that you're going to watch. In this case, the average number of people an infected person is exposed to daily, we're going to call E, and P is the probability of each of those exposures becoming an infection. Now, let's take a look at how this relates to the other function, because we're going to use some notation here that you're going to see that may be confusing, but it's just a different way of expressing the same thing. Oftentimes when we're talking about sequences, and you know we've learned about sequences like arithmetic, geometric sequences and stuff, and these are based off of geometric because it's exponential growth. But in sequences often in math, you actually use this kind of notation instead of like the function notation. And n would just stand for number, and the little subscript is like what we would normally use with the parentheses to represent the input. So it's really just like the same thing. So this is just saying the number of people after a certain amount of days. It's as if we did like n of d almost. And then n0 or n sub 0 just means the initial number of people that are infected on day 0, right? Okay, so this is the same as that, that's the same as that, and then you can see the 1 plus r, but instead it's 1 plus e times p. The real question becomes here, it seems like r and EP have to be the same thing. Does it make sense that the rate could be the product of the exposed people times the probability of each of those exposures becoming an infection, right? Well, I think that makes sense because let's just give a scenario. Let's say that let's say there's a person who's infected and maybe they're social distancing a little bit, maybe they're trying not to be exposed to too many people. And is this talking about new people? That's another question, because maybe there's people I'm repeatedly exposed to, maybe that makes a difference. So this isn't going to be a perfect situation, but let's just say E is equal to, I don't know, 4. But then for every time you are exposed to a new person, how likely is it that that person's going to actually themselves get infected? Well, again, we're just speculating. Let's say there's a situation where, in this case, the probability of that happening is, I don't know, 20%. So I'll say 0.2. Well, then E times P is 4 times 0.2. And let's think. This is 20% of 4. 10% of 4 is 0.4. So 20% is 0.8. So this is going to give me 0.8 or 80% of a growth rate. Now that seems to be a pretty steep rate, but again it does make sense because that's a probability, and since you're talking about the number of people an infected person is exposed to daily, maybe 4 is really high, but again it depends. Are we assuming infection? If you're infected, you know you're infected. In this case, a lot of people don't know they're infected. So maybe that would be lower, I don't know. Maybe the probability of somebody becoming infected once they become exposed, that might not be as high as 20%. It may likely be lower. Because if my growth rate was actually 80%, remember the last example, we just had it at 12%, that'd be super high. But in general, we can kind of see that this does make sense, that this works. And I just want to make sure you're okay with this notation. And you should be okay going through and finishing taking the video notes with the rest of this note-taking guide.